Hello friends, myself Dr. Nandakumar Raubavale from College of Engineering Ambazogai is going to deal with Applied Thermodynamics 2. This is our 7th lecture. In previous lecture we have discussed about chlorofluorocarbons which have the influence over the ozone layer, then pH diagram and components of vapor compression refrigeration system such as compressor, condenser, expansion device, evaporator, and working of vapor compression refrigeration system and the coefficient of performance of vapor compression refrigeration system. So today we are going to discuss about the numericals on vapor compression refrigeration system. So now we'll see one numerical problem on vapor compression refrigeration system. So in this problem, what is given? A vapor compression refrigeration system works between the pressure limits of 60 bar and 25 bar. So lower pressure is 25 bar and higher pressure is 60 bar. So P2, higher pressure is P2 is 60 bar and lower pressure P1 is 25 bar. The working fluid is just dry at the end of compression. That means when the refrigerant is compressed in a compressor, at the end of compression means at point 2, the dryness fraction of this refrigerant X2 is equal to 1, that is just dry at the end of compression, and there is no undercooling of liquid before expansion valve. So at the end of condensation, so this liquid becomes refrigerant becomes a saturated liquid, and from that point itself the refrigerant is expanded. So he is asking us to find out COP of the cycle and capacity of a refrigerator. So capacity of refrigerator is asked, that is in terms of refrigeration. Then he is giving one more data, that is the fluid flow is at the rate of 5 kg per minute. Fluid flow in the sense, this is the mass flow rate of refrigerant. Mass flow of refrigerant is given. So now let us collect this data and we'll have a plan for simplification of this problem. So now what is given here, initially he says that the pressure limit is 60 bar and 25 bars P1. So pressure P1 is 25 bar. So this is constant pressure process. P is equal to 25 bar. P1 is equal to P4 is equal to 25 bar. So P1 is equal to P4 is equal to 25 bar. Then at the end of compression, pressure increases and that pressure reaches to 60 bar, where the pressure at the point 2 and at point 3 is same. So P2 is equal to P3 is equal to what it is given, 60 bar or 50 bar, 60 bar it is given. So this is 60 bar. And then mass flow rate of refrigerant is 5 kg per minute, and dryness fraction at the end of compression, that means when the refrigerant is compressed in compressor from point 1 to point 2, at the end of compression the refrigerant becomes dry saturated. It is not going to become superheated or it is not going to become wet, just it becomes dry saturated. So this process 1 to 2 is shown on pH diagram here, 1 to 2. So this is pH diagram and this is pH diagram. So now what he is asking us to find out coefficient of performance and capacity. Two things are asked. So coefficient of performance, as we define as refrigerating effect divided by work done. So refrigerating effect in the sense the amount of heat absorbed in this condenser during 4 to 1. So that is nothing but enthalpy difference from H1 minus H4. H1 minus H4 is the refrigerating effect which is given in kilojoules per kg of refrigerant. Then work done. So work is done in the compressor from 1 to 2. So enthalpy difference, that is H2 minus H1, gives us work done in kilojoules per kg. So this process 1 to 2 gives us the work done in the compressor. So this process 1 to 2 is shown on this pH diagram here. So now work done in kilojoules per kg is given by H2 minus H1. Now if we know H1, then H2, H4, we can find out work done as well as the refrigerating effect and then COP of refrigerator. Then first we will find out H1. So to find out H1, so what we need is H1 is equal to HF1 plus X1 HFG1. So it is a wet condition of refrigerant is wet. So we have to find out this what you call enthalpy at point 1. So to find out enthalpy at point 1, so HF1 enthalpy of liquid at pressure P1 and dryness fraction of liquid at point 1. So this is X1 dryness fraction and HFG1 at pressure P1 bar. So here this HF1 HFG1 can be referred from properties of this refrigerant. So properties of refrigerant are given here, or sometimes the name of refrigerant will be given. So here name of refrigerant is not given, so therefore these properties are given in problem itself. So here at 60 bar all other properties are given. So here you can see HF is given. So at 25 bar at pressure P1 is 25 bar. So all these properties which we call as HF1, HFG1, SF1 and SFG1, these are given in this table corresponding to this 25 degrees Celsius. So now these are the things which are given, but what we don't know is X1. So to find out X1, we have to equate entropy at point 1 is equal to entropy at point 2. So entropy at point 1 can be written as SF1 plus of X1 SFG1, which is equal to S2. Entropy at point 2 is SF2 plus of SG2. So already we have studied SFG. So this is SF2 plus of SFG2. So here we know SF2 and SFG2 corresponding to pressure P2. So these values are known from steam table. So this is SF2 and this is SFG2. So this value is SF2 and this value is SFG2 corresponding to pressure P2. And SF1 and SFG1 is also known to us. So SF1 corresponding to pressure P1. So P1 and P2. So corresponding to pressure P1, this is SF1 and this is SF2. These are known. So X1 is unknown. So this X1 can be determined, and HF1, HFG1 are also known to us. So here this is HF1 and this is HFG1. So these are known. So from this H1 can be obtained. So now we have to find out H2. So to find out H2 directly we can take HF2 and HFG2 at pressure P2 bar. So pressure P2 is 60 bar. So at pressure P2, HF2 and HFG2 are given in this property table. So these values can be substituted. So now H2 is known. Now what is to be calculated is H4. To find out enthalpy at point 4. So what we know, the process 3 to 4 is a throttling process, and for throttling process what we say, enthalpy before throttling is equal to enthalpy after throttling. That is nothing but enthalpy at point 3 is equal to enthalpy at point 4. So to find out enthalpy at point 4, it is better to find out enthalpy at point 3, because we know condition of refrigerant at point 3, it just is a saturated liquid. So refrigerant is a saturated liquid at point 3. Therefore, so the H4 is nothing but equal to enthalpy at point 3, and enthalpy of liquid at point 3 is nothing but HF3 at pressure P2. So at pressure P2 means at 60 bar. So this 151.96 itself is HF3. So substituting H1, H2, H4 in this, say, equation number, this is equation number 1, this is equation number 2, this is equation number 3. So substituting these values of H1, H2, H3, H1, H2 and H4 in equation 2 and 3, and then the values of equation 1, 2 and 3 in equation number 1, we get COP of this refrigeration system. Then to find out capacity in terms of refrigeration, so first of all we must know refrigerating effect in kilojoules per minute. So 1 ton of refrigeration, as we know, 1 ton of refrigeration is equal to 210 kilojoules per minute. So to convert this refrigerating effect from kilojoules per minute in tons, we have to divide it by 210 kilojoules per minute. then it is converted into ton. So to find out refrigerating effect in kilojoules per minute, first we have to find out this refrigerating effect in kilojoules per kg. That is nothing but refrigerating effect is produced between 0.4 and 1. So therefore, the refrigerating effect which is produced between 0.4 to 1 is obtained by H1 minus H4 in kilojoules per kg. And if we multiply it by the mass flow rate of refrigerant, then in kilojoules per minute, then we get refrigerating effect in kilojoules per minute. So kg and kg gets cancelled, then refrigerating effect we get in kilojoules per minute. So this refrigerating effect which we obtain in kilojoules per minute is substituted here, and then we can get the capacity of a refrigeration system in terms of refrigeration. This is the plan to simplify this problem. Now to simplify, in order to proceed, so as we know, we have to find out H1, H2, H3. So our aim is to find out H1, H2 and H3. If we know these three things, then we can simplify this problem very easily. So to find out enthalpy at point 1, enthalpy at point 1, that is H1 is equal to, we have to take HF1 plus of X1 HF G1. So this is at pressure P is equal to P1 bar, P1, that is P1 is equal to 25 bar. So pressure is here 25 bar. We have to take these properties at point 1. So now HF1 at pressure 25 is known to us. HF1 at 25 bar is 56.32 kilojoules per kg. Then HFG1 at 25 bar is known to us from this table, that is 266.26. So what is not known is X1. So to find out X1, we have to equate entropy, because this process 1 to 2 is adiabatic process, and during adiabatic process the entropy of a system remains constant because there is no heat gain or heat loss during this process. So Q, transfer of heat energy, is 0, therefore entropy remains constant, or there is no change in entropy, that is ds during the process is 0. So now we have to equate entropy at point 1 is equal to entropy at point 2. Why? Because this process 1 to 2 is a constant entropy process, that is the isentropic process. So to find out entropy at point 1, we can write equation as SF1 plus of X1 SF G1. So this data has to be taken at pressure P is equal to, that is P1 is equal to 25 bar, and then to find out S2, that is to be obtained as SF2 plus of SFG2. So here dryness fraction of steam, or refrigerant at point 2, it is a dry saturated, already it is given in the problem. At the end of compression, the refrigerant is dry saturated, that is nothing but dryness fraction X2 is equal to 1. So this X2 is equal to 1, that means it is dry saturated. So here there is no meaning to write X2 value in this equation. So this data has to be taken at pressure P2 is equal to 60 bar. So now SF1, we know SF1 is 0.226 plus of X1, then SFG1 is entropy at 25 bar, SFG is 1.024, X1 into 1.0204, which is equal to entropy at pressure P2 is equal to 60 bar. So SF2 is 0.554 plus of SFG2 is 0.4792. So from this we can find out entropy at point 1. Just we will calculate this. 0.554 plus 0.4792 minus 0.226 divided by 1.0204. So this works out as 0.79 is the dryness fraction of refrigerant at point 1. So we know dryness fraction at point 1, that is x1 is known. So now we can find out enthalpy at point 1. H1 is equal to HF1 plus of x1 HFG1. So HF1 value we know at pressure P1, and this is at pressure P2. At pressure P1, HF1 value is 56.32. 56.32 from properties table, and x1 value just we have calculated as 0.79 into HFG1. HFG1 from table we can take it as 266.26. 266.26 into 266.26 plus of 56.32. So then this we get as 266.94 kilojoules per kg. So this is H1. So this is one value which was required to us as H1. So now we want to find out H2. So to find out enthalpy at point 2, enthalpy at point 2, we can write it as HF2 plus of HFG2. So HF2 at pressure P2 is equal to 60 bar. We can take from this properties table P2 is equal to 60 bar. So at 60 bar, HF2 is 151.96, 151.96 plus of HFG2 at 60 bar is 141.33, 141.33. If we simplify this, it gives us 151.96 plus 141.33. So this is going to be 293.29 kilojoules per kg. So now we obtained H1, we obtained H2. Now we want to find out H3. So H3 is equal to HF3. So at point 3, if we want to find out the pressure is P2, so H3 is nothing but HF3. So HF3 is nothing but enthalpy of liquid is 151.96. So this is nothing but 151.96. So it is in kilojoules per kg. As this is a saturated liquid at point 3, so it doesn't add any latent heat. So latent heat becomes 0. That is nothing but HF3 plus HFG3. HFG3 at this point becomes 0. If it is in between, then that HFG will add. So here it is a saturated liquid, therefore HFG is going to become 0. So now we know H1, H2, H3, that is nothing but H4. So now to find out refrigerating effect, our aim was to find out refrigerating effect, work done, and then capacity. So now refrigerating effect is equal to, so where refrigerating effect is obtained between 4 to 1. So heat is absorbed by refrigerant during process 4 to 1. So here H1 minus H4 gives us refrigerating effect in kilojoules per kg. So H1 we know. So H1 value which we have calculated is 266.94. So this is 266.94 is the H1 value. 266.94 minus of H4 is nothing but H4 is equal to H3. So because enthalpy at point 4 is equal to enthalpy at point 3, because this is a throttling process. So 3, 4 is a throttling process, where what we say, the enthalpy before throttling is equal to enthalpy after throttling. So H4 is nothing but H3, and that H3 is 151.96. So on simplification, we get refrigerating effect as 266.94 minus 151.96. So this works out as 114.98 kilojoules per kg. So this is how we obtained refrigerating effect in kilojoules per kg. Now work done during process 1 to 2, that is compression. So compressor is going to do work during process 1 to 2. So this is the work done. So if we know difference of this, that is H2 minus H1, gives us the work done in kilojoules per kg. So this H2 is known to us. H2 is 293.29, and H1 is also known. H1 is what we have substituted here, 266.94. So on simplification, we get this work done as 293.29 minus 266.94. So this is going to be 26.35 kilojoules per kg. So now we know refrigerating effect as well as work done. So now we can find out the COP of a refrigerator, coefficient of performance, is equal to refrigerating effect divided by work done. So refrigerating effect which we obtained here is 114.98, and divided by work done that we obtained here is 26.35. Work done is 26.35 kilojoules per kg, 26.35. So on simplification, we get coefficient of performance as 114.98 divided by 26.35. The coefficient of performance is going to be 4.36. Now he is asking us to find out capacity of a refrigerator. So now refrigerating effect which we have calculated in kilojoules per kg, which is equal to 114.98. So 114.98 is refrigerating effect in kilojoules per kg. So refrigerating effect in kilojoules per minute can be obtained as refrigerating effect in kilojoules per kg into mass flow rate of refrigerant in kg per minute. So here refrigerating effect is going to be 114.98, and mass flow rate which is given in this problem is 5 kg per minute. So this is 5 kg per minute. Mass flow rate of refrigerant is 5 kg per minute. So here 5 kg per minute. So in this, what happens, kg gets cancelled and unit is going to remain as kilojoules per minute. So on simplification, we get refrigerating effect in 114.98 into 5. So this is 574.9 kilojoules per minute. Now he is asking us to find out capacity of system. So this refrigerating effect is given in kilojoules per minute. So 1 ton of refrigeration is equal to 210 kilojoules per minute. So for 574.9 kilojoules per minute, how many tons of refrigeration we get? So to find out that, so refrigerating effect in kilojoules per minute divided by 210 kilojoules per minute, then we get this in terms of refrigeration. So 574.9 divided by 210, which is going to be 574.9 divided by 210. So this is going to be 2.73 ton of refrigeration is the capacity. Now we can write answers like this. A refrigerating effect is equal to 114.98 kilojoules per kg, and work done, which is calculated as 26.35 kilojoules per kg. Then COP of a refrigerator is 4.36. Then we obtained capacity of refrigerator as 2.73 ton of refrigerator. So this is the specific answer of this problem. So he has asked us to find out COP and capacity. Coming to the next problem, we have another numerical to simplify here. So find out theoretical COP of for a CO2 machine working between temperature range of 25 degrees Celsius and -5 degrees Celsius. So in previous problem, pressure range was given, here temperature range is given. So temperature is T2. Temperature T2 is given as 25 degrees Celsius and T1 temperature is given as -5 degrees Celsius. So lower temperature is -5 degrees Celsius and higher temperature is 25 degrees Celsius. The dryness fraction of CO2 gas during suction stroke, that is nothing but at the inlet of compressor. So the gas enters with a dryness fraction of 0.6, that is nothing but x1 is given directly here, and following properties of CO2 are given. So here nothing is given at the end of compression, whether it becomes dry saturated or it becomes wet. So now we are considering the refrigerant to be wet at the end of compression. So now, so actually this is the first table. Table 1 is given. Table 1 is given in the problem. So table 2 is created for our convenience. So lower temperature is -5 degrees Celsius, higher temperature is 25 degrees Celsius, that is taken as it is. So now to know, so here some things are mixed here, enthalpy, then entropy, and entropy are mixed, and latent heat is given separately. So generally what we follow standard method is this is HF, the enthalpy of liquid, then enthalpy of latent heat of vaporization, then enthalpy of dry saturated vapor. So now here this color coding you can see 164 and 72. So this data is taken as it is here. So this is nothing but HF, enthalpy, which is given in this table. Then latent heat is given here. So this latent heat 117.46 and 248.76. So this is taken here directly. So then the sum of these two, HF and HFG, is Hg. So here enthalpy of vapor is directly given here. So enthalpy of vapor is given here Hg. So this data is taken directly here. So that is nothing but Hg is equal to HF plus of HFG. So this is completed. Now SF is given, entropy of liquid is given. So just I will change color. Just I change the color. Now this entropy of liquid is given. So this entropy 0.5978, so this is given, and 0.2862 is given. So this is taken as it is here. And after that, the total entropy is given, Sg. Entropy of dry saturated steam is given, Sg. So this is Sg. So you can see from color, pink color data is taken here, so to avoid confusion. So now Sg is equal to Sf plus of Sfg. So if you add these two, plus of this is equal to this. So this data is not given in this table. So subtracting Sf from Sg, you get Sfg. Sfg is obtained. Sfg is equal to Sg minus of Sf. Sorry, Sf. Sfg is nothing but Sg minus of Sf. So this Sfg is obtained as Sg minus of Sf. So from this last 0.9918 minus of 0.5978, we get 0.394. Or else this Sfg can also be obtained by Hfg divided by temperature in degree Kelvin. So Sfg for this is Hfg is 117.46 divided by temperature in Kelvin is 25 plus 273. So again this works out to be 0.394. So this Sfg can be obtained by two methods: dividing this enthalpy of latent heat of vaporization by temperature in degree Kelvin, we get Sfg, or else by subtracting Sf from Sfg, we get Sfg. So Sfg, again this is Sg, which if we see 0.9918 minus of 0.5978, again this works out as 0.394. So by two ways, from this enthalpy we can find out Sfg, or we can find out from Sg and Sf same. So this Sfg is obtained. Again similarly, subtracting this 0.2862 from this 1.2146, we get 0.9282 as Sfg. So this table is referred in further calculations. Now here a COP is asked. So to find out COP again, so here a COP of a refrigerator. So data given, initial temperature is minus 5 degrees Celsius, and after compression, at the end of compression, temperature increases to 25 degree Celsius. So T1 is given and T2 is also given. Instead of P1, P2, here temperature is given. So now to find out COP of a refrigeration system, so here one thing you can observe, at the end of compression, so this refrigerant is not going to be on this dry saturated line or saturated vapor curve. So this is just inner, on inner side, means this vapor at the end of compression is going to become wet. So here we have to find out dryness fraction of steam at 0.2 x2. Dryness fraction of steam or refrigerant at 0.1 is known to us. So dryness fraction at 0.1 is known. We have to find out dryness fraction at 0.2. So now here you can find COP of refrigerator is given as refrigerating effect divided by work done in the same way as that of first problem. So this is equation number 1. So refrigerating effect is given in kilojoules per kg. Just we find out difference of enthalpy at 0.4 and enthalpy at 0.1. So H1 minus H4 gives us refrigerating effect, and that is given by equation number 2. Then work done is obtained. Work done in kilojoules per kg is obtained by knowing enthalpy at 0.2 and enthalpy at 0.21. So if we subtract H1 from H2, we get work done. So here work done in kilojoules per kg is given by H2 minus H1. So to find out again H1, H2 and H4. So to find out H1, HF1 plus X1, HFG1. So here X1 is given to us, HF1 at pressure P1 bar or temperature T1. So at temperature T1 means at minus 5 degrees Celsius, and T2 means at 25 degrees Celsius. So HF1 is given here 72.57. HFG2 is given as 248. We can substitute. X1 is directly given in this problem as 0.6. Then we have to find out HF2. So to find out HF2, X2 is required. So to find out X2, we have to equate S1 is equal to S2. So S1 is taken at pressure or temperature T1, and SF2 and SFG2 are taken at temperature T2. So here X1 is known, SF1, SFG1 are known. SF1 and SFG1 are given in this table here. Now SF2 and SFG2 are also given here. SF2 at temperature T2 and SFG2 at temperature T2 are known. So X2 is unknown. So from this equation we can get X2. Once we get X2, we can find out H2. Then H4 can be obtained as H4 is equal to H3, and that H3 is nothing but HF3 at 0.3. So this gives us H1, H2 and H4, and from that we can find out refrigerating effect. So only difference between these two problems is, in previous case the condition of refrigerant at 0.2 was dry saturated, that is the value of dryness fraction at X2 was 1, but here X2 is less than 1 because it is not on this curve. So this is the difference between previous problem and this problem. So at the end of compression process, the refrigerant is going to remain wet, it is not going to become dry saturated. Okay, so now coming to this, what is our aim is to find out H1, then H2, and then we want to find out H4, that is nothing but H3. So to find out H1, dryness fraction, enthalpy at 0.1 is nothing but HF1 plus of X1 into HFG1 at temperature T1 is equal to minus 5 degrees Celsius. So HF1 is given at minus 5 degrees Celsius as 72.57 plus of X1 value is given as 0.6 in the problem. Dryness fraction at the suction of compressor is 0.6. Then HFG1 is 248.76. 248.76. On simplification, we get it as 0.6 into 248.76 plus 72.57. So this is 221.82 kilojoules per kg. So this is H1. So to find out H2, formula is like this: HF2 plus of X2 HFG2 at temperature T2 is equal to 25 degrees Celsius. So here we know HF2, we know HFG2, we don't know X2. So here equating S1 entropy at 0.1 is equal to entropy at 0.2, because the process 1 to 2 we see here is adiabatic or isentropic process. So entropy remains constant, that is S1 is equal to S2. So looking at TS diagram, we can say that the process 1 to 2 is isentropic process. Therefore, S1 can be written as SF1 plus of X1 into SFG1, which is equal to SF2 plus of X2 SFG2. So this first data is taken at temperature T is equal to minus 5 degrees Celsius, and this data is taken at temperature T is equal to 25 degrees Celsius. So SF1, if we take from this table, it is 0.2862 plus of X1, which is given in the problem as 0.6, SFG1, which is 0.9282, 0.9282, which is equal to SF2. SF2 is 0.5978 at temperature T2 is equal to 25 degrees Celsius, 0.5978 plus of X2 we don't know into SFG2 at temperature T2 is equal to 25 degrees Celsius is 0.394. Then from this we get dryness fraction X2 as 0.6 into 0.9282 plus 0.28 X2 minus 0.5978 divided by 0.394. So dryness fraction is going to be 0.6226. So as we know dryness fraction at point 2, we can find out enthalpy at point 2. So to find out enthalpy at point 2, we will see dryness fraction is 0.6226. So dryness fraction at point 2 is 0.6226. Then enthalpy at point 2 is given by HF2 plus of X2 HFG2. So HF2 enthalpy at temperature T2 is 164.77 plus of dryness fraction X2 is 0.6226 into HFG2 value is 117.46 at temperature T2 is equal to, so this is at temperature T2 or pressure P2, because temperature T2 and pressure P2 are going to remain constant during process 2 to 3. So this data is given based on the temperature. Now we can calculate this as 0.6226 into 117.46 plus 164.77. So this is going to be 237.9 kilojoules per kg. So now we know H1, we know H2, and we can find out H3. So H3 is equal to H4, and that is nothing but HF3 at pressure or at temperature T2 is equal to 25 degree Celsius. So HF3 at 25 degree Celsius is 164.77. So this is 164.77 kilojoules per kg. Now we can find out the refrigerating effect and work done. So now first of all we will have the values of H1, then H2 and H4, that is nothing but H3. So value of H1 which we obtained here is 221.82 kilojoules per kg. Then value of H2 which we obtained is 237.9 kilojoules per kg. And then H3 we obtained just now is 164.77 kilojoules per kg. Now refrigerating effect is equal to H1 minus H4. So in kilojoules per kg. So H1 we know 221.82 minus H4 is nothing but 164.77. So this is the refrigerating effect. We get 221.82 minus 164.77 as 57.05 kilojoules per kg. So this is refrigerating effect. Then work done is given by H2 minus H1 kilojoules per kg. So H2 we know as 237.9 minus H1 is 221.82. So on simplification we get this as 237.9 minus 221.82. We get it as 16.08. Then to find out COP of refrigerator, COP is equal to refrigerating effect divided by work done. So refrigerating effect which we obtained here is 37.05 divided by work done is 16.08. So this is COP 57.05 divided by 16.08. So this is going to be 3.54 COP. So this is the answer of a given problem. So here we stop, and in next class we will be looking at the problem where the refrigerant at the end of compression goes beyond this wet region and it comes into this superheated region. So if we compress this from 1 to 2, so refrigerant becomes superheated from 1 to 2. So that will be the next numerical we will be simplifying in next class. Thank you.